let's get this session started. My name is Pirama. I lead Android's LLVM team, whose mission is to bring the latest innovations in LLVM from the community and partners to Android. For the last few years, we've been working on enabling profile-driven optimization in Android, and I'm going to talk about it today. First, let's expand on the topic a bit. Profiles or execution traces are collected from when a program is executing in production, and these profiles can be used by the compiler to produce optimized binaries that are tuned towards those production scenarios. The scope of our optimization is native code in Android, which is written in C, C++, and Rust. We have already enabled several of these optimizations in Android and saw significant improvements in many top-level metrics. We saw an app launch time, which is the time it takes from when a user clicks an app to the first draw on the screen. That improved by 8%. Turns out that's a key metric for user engagement and revenue driver for applications. Our boot time improved by 3%. And benchmarks that were targeting the binder and hardware binder libraries, they improved by more than 14%. We also optimized our host toolchains that are used to build code that runs on the device. So optimizing the host toolchains improved our build speed by more than 25%. So my goal for today is to explain how we use ARM's hardware tracing technology to do this on Android, and also spark interest in partners and OEMs to try this on their own devices and enabling tracing whenever it's available on their devices. So I'll start with an overview of profile-driven optimization, and then dive a little bit deeper into how to do sampling-based profile collection in Android. I will then explain the current set of optimizations that we have on and wrap up with our future roadmap. So to understand how a compiler can use profiles, consider the code snippet on the slide. There are two nested if statements and a call to a function foo that is called when both A and B are true here. And the compiler has to decide whether the call to foo can be inlined. It can use a naive heuristic and assume that each branch is true with a probability of 0.5. So anytime we evaluate A, there is a 25% chance that foo gets called. And the compiler might decide that this is not significant enough and skip the inlining. If on the other hand, we have profiles that say that A and B are very highly likely to be taken, then foo is in a hot path, and the compiler can eagerly inline foo. On the other hand, if the profile says foo is in a cold code path, then it can skip the inlining, right? So the availability of profiles helps the compiler make informed decisions to extract as much performance as possible from the hardware. The efficacy of profile-driven optimization is enhanced by the presence of LTO, where the compiler can see all the functions that are being linked, and those are available during code gen. So the compiler has more opportunities to do inlining, and it can make better decisions for inlining based on profiles. There are many other optimizations that are unlocked by profiles. For example, we can based on branch directions in the profiles, the compiler can lay out the branch instructions to match how the branch predictor will behave, thereby improving its accuracy. Functions and basic blocks can be laid out in a manner that take advantage of iCache locality. The compiler can eagerly do aggressive optimizations in hard code paths. It can do devirtualization, loop unrolling, and such. Or it can be conservative in the cold code paths, because like optimizations are always a trade-off, right? Like between code size, performance. So let me switch gears and explain how to set up a profile-driven optimization pipeline. There are three important aspects that need to be considered. First is to decide how profiles are collected. Um, one common method is to use instrumentation that will count um, how many times each basic block in the program is executed. But as you can imagine, this imposes a very high overhead of collection. Um, and we also need to set up a separate profiling pipeline and a testing pipeline for these instrumented builds. So the maintenance cost is also higher. The alternative is to use hardware-based sampling to profile the control flow. Since we are using hardware counters, the overhead of this collection is quite low, and we don't need a separate build. We can profile our release build and without extra setup. However, the profiles will be less precise than those produced by instrumentation, but we can bridge the gap in this by aggregating across a large number of sampling profiles. The next decision is to decide how we collect the profiles. If we have benchmarks that are representative for our workload, then we can use those. But we always run into the risk of overfitting to the benchmark, and the other case, which is more common, is that we don't have representative benchmarks for many of the programs we are looking to optimize. The alternative to using benchmarks is to just profile on the release build of the program. If it is a server workload, we can collect profiles from the data center, or if it is a client program, we can profile as it is running in our end user devices. And we can get precise user behavior. We don't need to rely on representation or from the benchmarks. We can collect actually how the program is being used in the wild. But if you are profiling released builds, there's always a delay between when we have a build available, when it is deployed, and profiles are available for use, right? So there is always the profiles are always from an older build, and software engineering never stops. So we have newer code base, and the compiler has to use heuristics to match profiles from an older build to the current build that is being optimized. The third aspect to consider is at what stage of the compilation profiles are applied. It could be done on the front end in the ASD, or in the back end in the IR, or it can also be done on the actual binary produced after linking. Front-end instrumentation is commonly used for source code and not for source code coverage and not for performance uses. By far, the most commonly applied techniques are on the IR and the backend. And like I mentioned earlier, combined with LTO, they get amplified performance improvement. Newer techniques like Bolt and Propeller take advantage of the fact that they can actually see the actual linked output and make changes to it. And as being the last tools that produce the binary, they can do more eager optimizations that extract the last bit of performance from the hardware. So in particular, like I mentioned, like optimizing in the backend is the most common. So AutoFDO is a specific name that is used to denote when sampling profiles are applied in the backend. And this is by far the most commonly used technique, and that's what we use in Android. So let me now dig a little bit deeper into how to set up sampling-based tracing in Android. The hardware capability in Android available in ARM chipsets for sampling has been evolving over the last few generations. Initially, around 2021, we started having chips with ETM and ETE that provide sampling branch records. They were really tied to the JTAG debug interface, so they were not really ready for production uses. Newer extensions like TRBE and BRBE are more suitable for more suitable for production use cases. In fact, we are working on enabling TRB in the next in a future Pixel device. We also need kernel support to take the data that is generated in the hardware extension and transfer it to the user space. For ARM64, it's done by the core side driver. And then we have the simple perf tool, which is equivalent to Linux's perf, which records and processes the traces on device. And all of this is managed by the prof-collect library in AOSP that triggers profile collection based on heuristics on what the device is doing right now. And it also takes care of uploading the profiles to the servers. So like I mentioned, we have ETM and ET on in our internal test population. It consists of around thousands of users, and we have used profiles from that to optimize Android user space. From the very beginning, we have worked closely with ARM's toolchain and kernel teams to, as we brought up ETM and ETE, and we got significant help from them to land this. As I mentioned, like there are multiple revisions of these hardware extensions, and each bring up is non-trivial. Every time we have issues in the core side driver, for example, there are two kernel patches from my team on the slide that fix some of the hangs we saw in the latest when we try to enable TRB. And so I'd like to call out and say, like, thank all the kernel maintainers from ARM and Linaro who helped review and discuss these issues. So okay, so let me wrap up with how with the current state of optimizations that we have on in Android. So we have AutoFDO on for 22 performance critical libraries in the Android user space. These profiles are collected from our internal test fleet of around 1,000 users. We have also worked with the kernel team in Android to enable AutoFDO for kernel 6.6 and 6.12. We did not use our test populations profiles for this because they're always on a limited, narrow range of kernel builds. But GKI at any time has multiple kernel branches and monthly releases that need to be supported. So we have a synthetic way of collecting profiles, which kind of mimics user behavior. It kind of launches many important apps and tries to do directed engagement on them. So we have AutoFDO enabled kernel builds for 6.6 and 6.12 branches. They are available in ci.android.com. We are doing more evaluation of this and hope to turn this on by default in a future GKI release. And if you have any partners who want to test these on your devices, please test and let me know. Let us know. We'll love to have feedback from you. So I'd like to come back to the point of like how our host toolchain optimization improved speed by 25%, because that's the ideal case of AutoFDO, where we have a CPU bound workload where the whole stack is optimized. That's not really the case in Android because we have a lot of managed code in Java and Kotlin, and also we have just not optimized the whole stack yet. We have native apps. We have the rest of the libraries in the platform. We have kernel modules. We have vendor libraries, and so one of our goals for the next few years has to enable AutoFDO in as many places as possible so we can get close to the 25% benchmark. So yeah, so I'd like to wrap up with what our roadmap is for the next few years. We are working on enabling TRBE in Pixel devices, and we would like to work with partners to enable TRBE and BRBE devices as they become available. This will enable us to profile from the fleet, from the billions of Android users, right? and this profile availability will help us optimize Android apps. In particular, games have a lot of native code that could benefit from AutoFDO. We would like to bridge the gap and optimize the rest of the Android platform, add more kernel modules to the mix, and also help vendors optimize their vendor libraries. And then the third pillar is to explore the newer post-link optimization techniques like Bolt and Propeller and see how they are relevant to Android. Yeah, so that's my overview for today, and I can take questions.
What does Bolt and Propeller do? Just improve locality?
They improve locality, and they also have so the profiles are collected in the binaries, right? And so after more inlining and all, like, you know, all the compiler optimizations have happened, and when we try to map it back to the IR, a lot of information is lost. So for example, like at the when profiles are applied, there is no inlining has happened, right? So if a function gets inlined into 5 different places, all of them get mapped to one location in the IR. But for Bolt and Propeller, they can see and operate and optimize each of the 5 different copies separately. So that is one, and they can do better layout. And they can reorder, they can do basic block, like function splitting, so that if there are 10 basic blocks and only 5 of them are hot, they can be together and the other 5 can be like placed somewhere else. Um, they can do a lot more because there is no linker sitting after them to meddle with things. Yeah, sure.
Could you please give more details about your daily collection of profile using 1,000 of internal users?
Sure. Yeah. So we have a continuous testing population, right? So we have like we send them like a new build every week, typically on Fridays, and on a mix of devices, not just the latest pixel, like on a mix of pixel devices, and people, and then we usually wait for a couple of weeks to get critical mass of profiles, because people take OTAs at different times, and we have requirements on how many users or how many reports are enough to kind of say that we have enough data. Any other questions?
Okay, so another one. You said that you use also profile-guided optimization and toolchain for building faster. So I guess you train the toolchain once every release or something like that.
Yeah.
So I guess the speedups are constantly decreasing after that, waiting for the next training when the profile become less and less precise.
So yes, so that is common, right? When as we use the same profile on newer source code, the performance improvement starts going down. We evaluated on the kernel. I think we saw across 4 or 5 weeks of kernel changes, we did not see as much degradation, but there was still a degradation. It was not stable. For the toolchain itself, we don't do like so we have more control over the toolchain, because every time we do an LLVM update, we kind of get the profile, and then 3 months later we come back to a new version of LLVM and we can get the profile. We don't profile from our users. We can just build AOSP with an instrumented build and collect profiles. Okay. Thank you. Thanks, everyone.